Hello everyone. We come to the fourth part of our introduction to recursive formulations for algorithm design. Just to recapitulate, our process is to develop initial solutions through a recursive definition, get a proof of correctness, analyze the whole algorithm through recurrence relation, explore the possibilities, decompose or unfold the recursion tree, examine the structures, recomposition, how the solutions are formed from the solutions of the subproblems. Then we see how do we choose, whether we have to have balancing of the split, whether we have identical subproblems, and today we shall see another aspect of it. In addition, we have seen that we may require data structures to remember the past computation and how much of additional space we require as we proceed. Today we will also look at 5a and b, and therefore the problem that we shall choose today is a very interesting problem. The problem that we choose today is called the coin selection problem. So what is the coin selection problem? Given a set C of n coins having denomination values C1 to Cn, and a desired final value of V, our goal or the problem at hand is to find the minimum number of coins to be chosen from C to get an exact value of V from the sum of denominations of the chosen set, of the chosen subset. Let us see what is an example. So suppose our example C is equal to 8, 6, 5, 2 and 1, and V is equal to 11. Then we know that we have two solutions, S1 which is 8, 3, 1, and S2 which is 6 and 5, and since we are to find the minimum, this one is our minimum. There could be a case where for the same example, suppose for the same example, instead of giving this value, we give some other value, and that value may not be obtainable. That means there may be no subset which obtains exactly the value that we want. So such a situation, the problem will return nothing. So now our objective is, our steps are Our objective is that from this problem statement, how do we get our recursive definition? So, in order to get our recursive definition, let us define the arguments of our recursive definition function. So, the arguments that we shall define coins S T X Z N, where S is the set of coins selected till now, T is the remaining set of coins from which we can select. X is the value of set S. Z is the remaining value desired to be chosen from T, and N is the number of coins selected. Some of the arguments are redundant, obviously. You can calculate the value of X from S, N from S, etc. But we are just doing this for our purposes of designing the algorithm. What is our case? How do we call it? We will call it with coins null, but initially we have nothing chosen. The remaining set is C as given in the left. The initial value is 0. The required value is V, and the number of coins chosen is. So, this is how you will give the initial call. This is how it will be called. And now we have to identify from our algorithm requirement, we will have to identify our base condition and our recursive condition. So, how do we define the base condition? How do we define the problem and define a recursive decomposed solution for this problem? And what will coins return? Coins will return a set that has been selected and the number of coins that have been selected, and we want to do it in such a way that it is the minimum of all those which have been selected. So, now we come to the algorithm. So, as we said, our algorithm will return PD is equal to coins S T X Z N. So, P is the set return, D is the number of coins. So, now how is our algorithm going to proceed? So, let S is equal to S1, S2, Sn, T equal to T1, T2, Tm. Now we start writing our base conditions. So what are our base conditions? Our base conditions are, if z may be 0, z may be negative, or t may be null. So the first thing we check is if z is equal to 0, which means that we have found that whatever is there in S has actually returned our required value. That means there is no more value to be chosen. So if that is the case, we return Sn, because capital S now contains all that we wanted. The other thing that can happen is, if z is less than 0, then you return and the third thing is if t is equal to null. And if we reach the point here when t is null, we know that z is positive, because z is not 0, z is not negative, z is positive, but t has become null. So in this case again we return a failure, saying that there is no solution, because we now have a situation where we have t becoming null, but z is non-null. That means we still have some remaining values to get. Now if that is the case, then let us see what will be our recursive condition. But prior to writing our recursive condition, we will also initialize p min, that is the final minimum, to null, and the number of coins to be chosen to be infinity. That is whatever the value will return. Now the idea is that we will choose every coin from t and add it to S and recurse. That means we will choose one by one, we will choose one coin from t, add it to S and call the recursion. And we will do this for every value. We will get the return values from here, and from these return values we will find the minimum. So if we are to do this, so we will do for I equal to 1 to m, that means for all values of t. That means we are going to choose elements of t one by one. What we are going to do is we are going to add that value in S. We are going to remove that value from t, and we are going to call, we are going to get the value p dashed d dashed and call coins. We are going to call coins with w, u, x plus ti, z minus ti, and since we have chosen one more element, plus 1. And once we have done this inside the loop, what we will do is we will now check whether if D is less than min, that means if we have improved, then we will find min equal to D and update P min, if D dashed, this is D dashed equal to P dashed. This returns here, this comes out of this loop, and we return P min and min. Just to repeat, what we are doing is, for every element in T, we are creating a set W by adding Ti to S. We are creating a set U by removing Ti from T, and we are recursively calling it on this new set. Whatever we get, we are now seeing whatever is the value returned. Based on the returned value, over this loop for I equal to 1 to n, we compute whatever is the minimum, and having computed whatever is the minimum, finally the minimum is returned. So this way we have now computed the minimum of all ways in which I can add one element into the set from the previous set. So this is how we compose we now work out the previous algorithm that we just discussed using an example. So the example that we had seen earlier had 8, 6, 5, 2, 1. Initial set is S is null. This is the available set T. The value obtained till now is 0. The required value is 11. The number of coins chosen is 0. Now we can break this up by choosing, in that for loop we can choose 8, we can choose 6, we can choose 5, we can choose 2, and we can choose 1. This is how the for loop of this algorithm goes. In this for loop, for every element in T, we will add it to S to form W and delete it from S to form U. So if we do that, then in this case what we get here is 8 comes here, 6, 5, 2, 1. Value 8 is chosen, 3 is remaining, 1 coin is chosen. Similarly here we get 6. Here the remaining values are 8, 5, 2, 1. The value chosen is 6. Remaining value is 5. 1 coin is chosen. Similarly, in this case, we will get 5 is chosen. The remaining elements are 8, 6, 2, 1. The value 5 has been obtained, 6 is remaining, 1 coin is chosen. And we will get this and this. I am not doing these two. Now if we break this up, then here again we have 6 can be chosen, 5 can be chosen, 2 can be chosen, and 1 can be chosen. We know that if we choose 6, then this will be 8, 6, this will be 5, 2, 1. The chosen value is 14, remaining value is minus 3, number of coins is 2. And we know that if we call this with a negative value, then as soon as it reaches a negative value, the base condition returns null. So this here it is 0, and from here a null infinity will return. Similarly, we can see the same thing will happen here, and from here a null infinity will return. But that will not happen when 2 is chosen, because when 2 is chosen, then you will get 8, 2, the remaining value will be 6, 5, 1, 10 has been chosen, remaining 1, 2 coins are chosen. This is what happens. Similarly, for this case, we will have 8, 1, we will have remaining values are 6, 5 and 2, 9 has been chosen, 2 is remaining, 2 coins are chosen. And here again there are two options. You can choose 6, you can choose 5, and you can choose 1, and it will easily show you that if you choose this, here again from these two both null and infinity will come out, whereas from this part will yield 8, 2, 1, it will yield 11, sorry, the remaining set will be 6 and 5, it will yield 11, 0 is remaining, and 3 coins are chosen. And we know that this is a solution, because in this case z is 0, and we know when z is 0 we return Sn, and what will be returned here what will be returned is the set S8 to 1 and 3. This will be returned from here, and because the other two brethren are like this, from here again we will get the situation of the same value here 8 to 1 and 3 will be returned. It is not difficult to see that from 1, which is the other remaining branch, that is from this remaining branch, you will again get back this thing, and when this branches out, this will branch to 6, 5 and 2, and we can always see that both this and this will yield failures, whereas this one will again yield 8, 2, 1, 6, 5, 11, 0, 3, and this will return the same solution as the previous one. It will return 8, 2, 1 and 3. It is not difficult to see that from this case you will actually get 6, 5 and 2 returned. From this case again, from this case I am not drawing the details of the recursion. You will get 6, 5 and 2 returned. From this case, you will get the same thing again returned, because 2 is chosen, and since 2 is chosen you will again get a solution 8, 2, 1, 3 from here, and from this case you will again get 8, 2. I have not worked out each of these steps, but this is what we will get. And this will therefore also return, this will also return 8, 2, 1, 3. This will return 8, 2, 1, 3. And given all these, this option, so the solution to this problem will come up as 6, 5, 3. This is the final solution. So this solution will come. Now what I leave to you to prove are the following. 1. Proof of correctness. That it will yield the correct result. Second is the complexity, time complexity in a recurrence. This we will discuss in the class in more details, but let us analyze this a little more carefully for our next analysis. And our next step is analysis of the recursion tree. If we analyze the recursion tree, you will notice a very interesting thing. What will you notice? You will notice identical subproblems. This combination are all identical subproblems, and these identical subproblems will come. This combination of 6, 5 and 2 will not only come from the 6th branch, it will also come from the 5th branch, and below you will have multiple identical subproblems. So once we analyze this, we see that though this recursion is correct, its time complexity will be huge if we do not address the issue of identical subproblems. So how do we address the issue of identical subproblems? We can use the same approach that we had used earlier of using a done array, where we check whether the arguments s, t, x, z and n are identical, and we store all the recurrence calls for this, and whenever there is an identical call, we just check whether it has been done like the method we used before, and then based on whether it has been done or not, we then immediately determine how we are going to address this identical subproblem issue. The other alternative is that can we modify the recursion in such a way that these identical subproblems are not generated. So how do we do this? So let us go back and look at our recursive definition. The recursive definition that we had was, we are removing one element at a time and adding it, removing it from T and adding it to S. Now if you notice here, when we removed 8 here, then the combination 8, 6 came this way. The 8, 6 combination will also come from the 6, 8. The 5, 6 combination will come from 6, 5. The 8, 2, 1 combination will come 8, 2, 1, 8, 1, 2, 1, 2, 8, 1, 8, 2. All these combinations will come. So we could avoid that. Can we avoid that? So what we can do to avoid that is our question. A simple thing to avoid that will be to address the recursive condition in the for loop. And we want to ensure that if we choose 8, we remove 8. When we choose 6, 8 does not exist. That means the combination of 8, 6 will come this side. 6 is chosen first, then 8 is removed. So in order to do that, all the changes that we make in the recursive condition is that at this part where we are doing s equal to s minus s plus ti, which is fine, we are adding ti, but when we remove from u, we make a different change. So what is our improved alternative definition? Everything else remains same. Instead of u equal to t minus ti, we do the following. What we do is u is equal to t minus t1, t2, ti. That means we remove all the other elements. So when we had our example, in our example, when we had our example of 8, 6, 5, 2, 1. In one case, when we chose 8, this had null, this had 0, this had 11, and this had 0. This was our definition. When we chose 8, when we choose 6, and when we choose 5, when we choose 8, we make it 8. Then here we have 6, 5, 2, 1. and we have chosen 1, we have to remaining 3, we have already chosen 8, remaining 3 and 1 coin. When we choose this one, we not only choose just 6, but here we remove not only 6, we also remove 8, as has been depicted here. So this becomes 5, 2, 1. It becomes 6 has been chosen, 5 is remaining, 1 coin is chosen. When we choose 5 here, we choose 5 and this just becomes 2, 1. And we have chosen 5, we leave 6 and we have chosen 1 coin. Now that we have such a situation, we can clearly see that identical subproblems that were generated earlier will not be generated now. So now again 2 more things are to be done. What are they? 1, proof of correctness. Second is time complexity based on the recurrence relation. The third is analysis of recursion structure. Does this recursion structure still yield any other possible identical subproblems? Or identical subproblems will never be generated? So this is the other question that we have, and I will leave it for you to think about the answers to this question so that we are able to discuss this in more details in the. Instead of trying to look at it by only one method of recursive definition, we are now trying to look at another way of developing a recursive definition. And this new recursive definition, so this is the recursive condition. This new recursive condition will be based on the inclusion exclusion principle. And through this inclusion exclusion principle, we are going to now not in a for loop do every element from T1 to Tm, but we will look at only T1 and decide to generate 2 subproblems. One to select T1, the other not to select T1. So how do we do that? So we generate 2 subproblems, one by selecting T1. So we to take T1, we remove T1 from T, it gets added to the value, it gets deducted from the value, and n is incremented by 1. So this way I have chosen T1. The other, I decide not to choose T1. So here I will call coins 2, and S will remain as it is, but T1 will be deducted from T. X will not get added because I have not chosen T1, and Z will remain as it is because that is the amount that I still have to do, and the number of coins chosen is still n. So one is inclusion, one is exclusion, and then I choose the minimum of whatever I get from this side and from this side. So now I do if, so the method now is if D1 is less than equal to D2, I will make P min equal to P1 and min equal to D1, else P min equal to P2 and min equal to D2. And I will return as before P min min. So this is the alternative definition, and in this alternative definition, all we do in this alternative definition is we make sure that we are going to only choose one side and the other side. So let us just quickly run through our example. Our example was null 8, 6, 5, 2, 1, 0, 11, 0. Now at every stage, at level 1 we decide on 8. So this is 8 is taken, here 8 is not taken. So if 8 is taken, then this becomes 8, this becomes 6, 5, 2, 1, 8 is chosen, 3 is remaining, 1 coin is chosen. If 8 is not taken, then this remains null. Again 8 is removed here. As you can see, it is removed because 8 is no longer going to be considered at the next level. So this again becomes 6, 5, 2, 1, but this is 0, this is 11, and this is 0. And in the next level 6, it could be in any order, but now 6, here 6 is taken, not taken, here 6 is taken, not taken, and so on and so forth. And therefore you will see that the subset T at every level remains the same. At every node, at every level, the subset T remains the same. However, the subset S, which is chosen or not chosen, varies depending on whether it is chosen or not chosen, and the rest of the values change. Therefore, the value of T is again not done. So here again, as we have seen in this definition here, this new recursive definition, we are left to analyze 1, inductive proof, 2, time recurrence, 3 identical subproblems. These are the 3 things. We have to do an inductive proof. We have to determine the time recurrence of this problem, and we have to check whether identical subproblems are generated or not. And we leave it to you to think about this, and we will discuss this in more details in the class, and you can work it out and come with your questions on this. Having said this, now we come to the most important thing. Let us look at a scenario like this. We are at a node here, and say it has branched to 3 places in this problem, whichever method we use. In one it will be branching to multiple, the other it will be branching to 2. And as we move ahead, at some point we reach a goal solution. So a goal node is reached, a terminal node is reached, and a solution is reached. For example, here in this case we reached a solution of cost 3 here, and we will reach various solutions of cost at various places. So let a solution cost equal to x. Now, at any point in the subsequent search, the solution at an intermediate node, which is this value, the number of coins chosen here, that is the number of coins chosen, because that is the one which we have to minimize. So suppose at any point here the number of coins is y, and we have x is less than or equal to y, which means that our previous solution, the current solution that we have obtained, this solution is at least as good as the coins already chosen at this stage. And the number of coins that chosen at this stage can only remain the same or increase. So if x is already less than equal to y, we need not search further, and we can prune or discard the searching of the space beyond this point. So if we are traversing this in a depth first manner, then during this depth first traversal we can do a pruning. And how do we do this pruning? So we do this pruning in the following way. We maintain a global current best. So CB, which is initialized to infinity. So it is initialized to infinity prior to the search. Then this recursion is evaluated in a depth first manner. That means we go this way, then we go here, we find the solution, then we come here, then we come here, then we go back, then we come here. So we go in a depth first manner. During this depth first manner, we update our base conditions. So the base conditions are revised for pruning. The base conditions are revised for pruning. How are they revised for pruning? If z equal to 0, then we now check, because this coins, we now check if n, which is the solution at z equal to 0, we check if n is less than Cb, that means that this new solution is better than the current best, then we update Cb equal to n. That means we update the current best, which means that if at some point in time we get another solution here whose solution cost is W, and this is a goal node, terminal node, and we find W is less than X, then we update current best to W. Because we first had current best, initialized current best to infinity. When this is the first solution we got, current best became X. When this is the second solution we got, then current best became W. And if X is less than Y, obviously W will be less than Y, and we will prove. So here is where we update the current best. And we also will return, because we are updating the current best, we will have to return. So we don't have this bracket closed here, because this is not a bracket closer. This, and so we have updated the current best. We have updated the current best, and then we return S so we update current best. If this happens, we update current best and we return S n as before. The other case is if if z less than 0. If z is less than 0, then obviously we will return null infinity. If t is equal to null, again we will return null infinity. because now z is positive, z is not 0, z is not negative, so z is positive and t is null. The other option where we will now get is another new condition. We will check if n, this is the condition, this condition we will check now. If n is greater than or equal to current best. Now again here also now we know that we don't need to go further because this is worse than the current best, and this is not a solution, because if it was a solution then z would have been 0. So here again we will no longer need to search this part, we will return null infinity. And this part is what we call our pruning step. This is our pruning step. So this sort of a pruning during the traversal will enable us to ensure that we do not see places which are not to be seen. So let us go back and look at this example. Here in the base conditions that we had, when we found the base condition with z equal to 0, we updated it with the current best. If z is less than 0 or t is less than null, that is nothing to be done. But the new condition that we have added for pruning is this. So this is the new condition and this is the pruning condition that we have added. So this is how we are able to add pruning to the tree. I will request you to try and work it out on the example. So here is another thing, work it out on our example. Work it out on our example and see what sort of pruning we are getting, if at all. So based on this, we now finalize our algorithm, and in order to finalize our algorithm, obviously we now have two options. We have two recursive definitions of recursive definitions. And for these two options of recursive definitions, we have to analyze each one of them and see which one of them is better or are both identical. And then we apply the pruning technique that we have introduced if we do a depth first search. And this sort of a pruning, when we do a depth first search, leads to a very interesting methodology in algorithm design called depth first branch and bound. And if we do a more advanced search, which is out of the scope of this course, then it comes to what is called a best first branch and bound. And maybe if we get some time, we will discuss this in a little more details. We also need to see if identical subproblems arise. And based on this, suppose we choose the second option, then we would introduce this pruning condition here, and with this new pruning condition included in this algorithm, we would add the pruning condition in this algorithm, and I leave it to you for an exercise to include this, try and develop a code and execute the code. Finally, there are several special cases. Let me introduce a very interesting special case. The interesting special case that I would like to introduce is, let us consider an example where my set C is of 16, 8, 4, 2, 1, and I have to get some value. Whatever value I have to get, because as you can see it is in the powers of 2, you can check that if the V, I will choose, given the value of V, I will choose the largest one first. The largest one that is not equivalent to the, that is less than or equal to the value of V. And among the options that I had here, if you notice, I could have chosen here 16, 8, 4, 2, 1. Among these options, if it is of a form like this, then among these options, and suppose V is equal to 25, then among these options, whichever option I choose, I can prove that the choice for 16 will be part of optimal solution. That means that I will then just decompose the problem to 8, 4, 2, 1, having chosen 16. Having chosen 16, I have got 16, and if I remove 16 from 21, I get 9, and I have chosen 1. Now here I have options of choosing 8, 4, 2, 1. Again I can prove that because 9 is remaining, if I choose 8, then I will get the best solution. So the others can all be rejected. These can be rejected, these can be rejected, these can be rejected. That means among the various options, in this particular case, the next is 16, 8, and it will be remaining 4, 2, 1. I have chosen up to 24, remaining 1 I have chosen 2 points. Now I have options of 4, 2, and 1, but 4 and 2 are not applicable because choosing them will make z less than 0. So I will choose 1, and if I choose 1, then immediately I find my solution. So here I see that there are special cases in which in these special cases, we can make a single choice from the various recursive subproblems. And this single choice can come for special cases. This, as you can all see, is very much related to the binary encoding system. But if you notice our common coinage problem, where we are given a set of coins, and if we are allowed to choose any amount of the same coin, see our coinage system has got 100, 50, 25, 20, 10, 5, This was our original coinage system. I don't know whether you still see 3 paisa or 2 paisa coins, but this is the coinage system that we had. And you can see that if you have sufficient supply of all of them, then any number can be made by such a choice of any one of them taken quickly. So the coinage system is designed so that the algorithm does not have to explore options. That is another way of looking at it. So this is the third thing that we saw. We saw that in many cases among the branchings we are able to make a particular choice upfront based on the problem specific domain. This leads to another paradigm of algorithm design. So in summary, we have seen that we can get our initial solution. From this initial solution, we have the options of balancing the split. Where do we do the split? This one we saw for the max problem, the min-max problem, and the max 1, max 2 problem. Then we see we have the issue of identical. So this is when we analyze the recursion. Identical subproblems, where we will need memoization to remember those subproblems. The third is whether we can make a choice, which is often called a greedy choice, from the subproblems upfront. And the fourth is whether the traversal or evaluation of the recursion allows for pruning or preemption based on solutions already found. Thirdly, we need proof of correctness, and analysis of complexity, and design of data structures. This gives us a summary which we have seen through the following problems that we have done. The problems that we have done till now the max problem, the max min problem, the max 1, max 2 problem. Then we saw the fib series or the equivalent of the Fibonacci series. The third, we saw the coins problem. And we have seen that for the same problem, many recursive definitions can come, and the data structures, the recursion tree, and all of them built together. With this, we see some very simple problems, and based on these problems, we have now got an idea of how to develop these algorithms. So this will yield some of the core methods: the divide and conquer, the greedy algorithms, dynamic programming, and branch and bound. These are the four methods which are the core methods, which come from the balancing the split, or any recursive definition is the divide and conquer. From the identical memorization, we get dynamic programming. From the greedy choice, we get greedy algorithms, and from the pruning conditions, we get the branch and bound algorithms. These are the fundamental ideas which yield some of these problems. For analysis of complexity, we get recurrence equations, and as we are studying, we are going to do asymptotic analysis of the algorithms based on our ON and theta n and omega n functions. With this, we come to the completion of the introductory lecture, and then we will look at other more important problems like sorting, searching, patterns, trees, graphs, and other combinatorial optimization issues. Subsequently, we will discuss each of these methods, core methods, in more details, but approach it from this recursive transformation viewpoint. Thank you very much. Please feel free to ask questions, but please look at the issues that I have raised and not answered, and I have asked you all to do it on your own. Please do it and come, because these are the things that we shall discuss in the class.